No, no, I'm the speaker. Okay. Okay. Do you want to help pronouncing my name or anything?
Yeah, I will call everybody in.
Let's give it one more minute. Good afternoon. Please take your seat. And we will begin with the afternoon session. So our first speaker is Kat Barger. She's going to talk about the LMC galactic wind, which I think is very interesting. So Kat, whenever you're ready, thank you very much.
The Large Magellanic Cloud galaxy is bursting in stellar activity, and that stellar activity is driving a galactic wind from this galaxy. So we're going to switch it up a little bit, and we're going to move from the individual stars and look at the effect that massive stars can have on a galaxy-wide system. I'm leading a large Hubble Space Telescope Legacy Archive project to explore this galactic wind using the Ulysses dataset as background targets. And so this is going to be a little bit different from the previous talks in that I'm not using the stars to learn about the stars. I'm using the stars as background flashlights. That light travels from those stars to us, and there's an opportunity for it to interact with intervening material and get absorbed. And I'm using that absorption to learn about the intervening gas. Okay, so I'm using these stars as background flashlights to learn about the gas in front of it. And some of that gas happens to be a galactic wind. Okay, so I mentioned that the LMC is very bursty. What we have here on the left-hand side is a gas distribution map showing you the H-alpha emission, sulfur 2, and oxygen 3. And what this traces here is essentially the energetics occurring inside of the disk of this galaxy. The locations where there's H-alpha are locations where there's a lot of ionization, star formation, star deaths. Locations where there's the oxygen 3 are the more extreme energetics. What we have on the right-hand side is we have a distribution map of what is going on with the gas flows. Chris Hauck and Nicola Lenner, they went and they studied the outflows associated with the Magellanic Clouds using the same technique that we're describing today, but back in 2007 and 2002. And what they did was, using background stars in the LMC, just like we described, they found that in the directions of the LMC, there tended to be more blue-shifted material coming towards us than red-shifted gas. So that told us that there is outflowing material, preferentially outflowing material from this galaxy. Now, there's a lot of things happening with the Magellanic Clouds. There's also tidal debris every which direction and all kinds of fun stuff because we have the LMC, SMC, Milky Way interacting. So we have to convince ourselves that these outflowing material is associated with actually a galactic wind. So what we did was we did an experiment. This is an experiment I did back in my postdoc years, where what we looked at was in this direction over here, there happened to be not only a bright disk star, UV bright disk star in the LMC, but there was actually additionally in a background AGN. And the reason why that's important is because if we use a background AGN, we can probe the material on the back side of the disk of the LMC, in addition to the front side. And since these two targets are right next to each other, we could use it to figure out, well, what do the gas flows look like on the front? What do the gas flows look like on the back? And if this is indeed a galactic wind, then they should be relatively symmetric, as opposed to if it was related to all the other circumgalactic medium structures associated with these galaxies. So when we did that, okay, so here's a geometry where we have the LMC's disk here. This is our eyeball looking at it. This is what we're sensitive to towards the star. Here's what we're sensitive to towards the AGN. And here's what we saw with the spectra. On the top, here's the star. Here is the background AGN. What I'm showing you on the bottom, kinematic, where the kinematics corresponding to the disk of the LMC are colored in this gray swatch. And then over here we have apparent column density. This is absorption, but it's apparent column density, which is why it looks like emission even though it's actually absorption. Over here on the blue shifted side, towards the star, we see material. Towards the AGN, we also see material, but notice towards the star, there's nothing over here on the red shifted side. And over here towards the AGN, we have material that's red shifted. So what that means is on the front side, where we're sensitive to both the star and towards the AGN, we have this blue shifted material corresponding to wind approaching us, receding out of the disk in our direction. And on the back side, the red shifted material has to lie on the back side, which means that it's outflowing, but on the back side of the disk. And so this right here was convincing that all the outflowing material that we saw previously from earlier studies was indeed associated with a galactic wind, large-scale galactic wind. But that's not too surprising because this particular galaxy is very energetic. But what was a little surprising is that we see outflows in every which direction, even in locations where this galaxy is relatively boring. And so how are we getting these outflows in boring locations in addition to the more exciting regions? So after racking my brain a bit, I'm like, okay, what is happening here? Probably what is occurring is that you have locations where there's a lot of activity that kicks material out, and then it'll enter a region of low density, and so then that material is able to essentially just spread out and loom and thermalize. And so what can happen is that you can get a galactic wind across the entire face of the LMC, but that doesn't necessarily mean that the wind is produced at every location in the LMC, okay? It just spreads out once it escapes out of the disk. Okay, so one of the things that we did before this Ulysses study is that we wanted to map out this wind. So what my team did was using the Wisconsin H-alpha mapper telescope, we mapped out the H-alpha mission for just this galactic wind. The benefit of using mapped observations is that you can look at the morphology, the gas distribution in a way that you can't do so well with absorption line studies. Ulysses is a little bit different just because we have so many background targets. But most of the time, this was pre-Ulysses. It didn't exist. The concept didn't exist yet. Okay, so what we're looking at here towards the LMC, only gas that's associated with blue shifted kind of velocities approaching us, outflows. Oh, here's the pointer. Here we have the H1 disk is what the contours are tracing. This right here is a Magellanic Bridge. It's a tidal bridge that connects us all the way over here to the SMC. All of this right here, you're seeing H-alpha emission. What we're looking at right now is a particular channel map that's showing you the slowest moving part of the wind relative to the LMC galaxy. And if I move forward, I'll show you another channel map where we're going a little bit faster. A little bit faster still. And notice that there's one spot that is very, very bright that stands out the entire time. It's this spot right here labeled 30 Doradus. This is the very, very active region that is acting more like a starburst, mini starburst inside this galaxy. And so this right here is convincing evidence that in this direction, there is actually indeed a fast-moving component of this wind. Okay, So here, if we consider all of this material, the slow and fast-moving gas, to be associated with the wind, there's a tremendous amount of material being ejected, on the order of 85 million solar masses at a rate of roughly 1.4 solar masses a year for the entire wind, both the slow and the fast-moving component. Okay, so when we look at it, here's what we have for the total wind here in H alpha for the near side. Okay, now if we'll break it up into the slowest component and the fastest component here. Okay, so with the fastest part, there's less gas, not too surprising. You need to be going relatively fast to escape out of the galaxy. Over here, we have 30 Doradus. Interestingly, so with this scenario right here, what we would imagine is that we have a scenario where we have a cartoon situation where we have the Milky Way galaxy, pointer, doesn't point the direction you're wanting to point. Here we go. Okay, so we have the Milky Way galaxy over here. We have the Large Magellanic Cloud galaxy over here, and based off of this H alpha and based off of the absorption line studies we have a slower moving component represented by a lighter blue and a faster moving component represented as a darker blue. And so this is a cartoon that we would expect to have. However, that's not the complete story. The reason why is because right here in this particular direction, there happens to be a star right towards the edge of the LMC's disk. Remember, this is H1 contours. And at this spot over here, there happens to be a high velocity cloud with a known distance at 13.3 kiloparsecs or closer. It's a limit on the distance over there. So that tells us that there has to be some gas in this direction that is close to the Milky Way. So then the question is, okay, well, we have convincing evidence that it could also be associated with the wind, so what's going on here? All right, so to me, there's a couple of different scenarios. Okay, so here's the information that we know. We have the Milky Way over here. We have the stellar absorption feature that tells us that there is high velocity gas in this direction towards the edge. We have 30 Doradus over here, which tells us there is fast-moving gas associated with the wind. But at the same time, those other studies that we showed, including the H alpha study, but some work done by Chris Haug, Nicola Linner, 2007, and also especially their 2019 work, that tells us that there is a fast-moving component of something here. And that particular fast-moving component extends the entire face of the LMC, which is also what we see in H alpha as well. So we have a couple of scenarios. One scenario is that we could have a situation where we have a fast-moving gas that happens to be just near the Milky Way, that happens to cover the face of the LMC. That's a possibility. Okay, in that scenario over here, we might have some slow-moving wind, so the light blue, and some fast-moving wind in the 30 Doradus direction. So that's a scenario. We have another scenario over here where we have a situation where we only have a situation where we have a fast-moving wind here, and the fast-moving wind covers the entire face of the LMC. Okay, that's also plausible based off of the observations. And we have another situation where, guess what? We could have both. Both could also happen. So which one is it? Well, there's a debate in the field. I can't tell you what the answer is. I can tell you what different data sets are telling us, and what some of the data is telling us, that there is support that there is at least a fast-moving component part of this. And over here, there's a bit of a question mark. The support for a fast-moving component of this wind include, when we look at the H1 gas, there happens to be correlations with what's happening with where we see high regions of column densities associated with voids in towards the direction of the LMC. So that seems very consistent. So locations where there's a lot of activity, there happens to also be a lot of H1 fast-moving gas. Okay. There's also evidence when we look at the Lenner and Hauk 2007 study, and what they did is they looked at the line ratios of oxygen-6 and carbon-4, and they found that the ratios between the LMC and the fast-moving stuff relatively agreed with each other, and the ratios between the slow-moving stuff, the very slow-moving stuff that's more at velocities consistent of the Milky Way, intermediate velocity material is what that would be called, and the Milky Way gas, that also had relatively consistent ratios with each other, and they seem to be separate populations that seem to be relatively consistent with each other. So basically, in other words, if the material was moving slow, consistent with the Milky Way's motion, it seemed to be consistent with the Milky Way. If it was fast, then it seemed to be more consistent with the Large Magellanic Cloud galaxies. Another track of evidence is over here, the Leonard et al. 2009 study, where what they did was they looked in every which direction using fuse observations towards, I feel like it was 109 sightlines. I can't remember off the top of my head. But in that particular study, they found that there was a high covering fraction of 70% towards the direction of the LMC. And they also found a chemical composition that seemed relatively consistent with what could be an LMC origin. Okay, so relatively high at 30%. Remember, the LMC is at 50%. Now, there could be some issues with maybe some ionization corrections, but this is O1 over H1, so I don't think that that'll be the case in this particular case. But then depletion, there could be some issues with ionization corrections here. Based off of the sulfur ratios, sulfur to silicon ratios, it looked like there's dust in there. And the reason why we care about dust is because dust tells us that because dust is produced in galaxies, because they're produced by stars, there's so many star experts here, dust is produced in stars, that means that this material would have been having to be associated with a galaxy at one point. And so a galactic wind is a natural origin for that. Okay, so let's continue. All right, so the work that we're doing now with Ulysses, what we're doing is we're looking towards the 30 Doradus region. The reason why is because it happens to be very active, and it's a very exciting region. And so we know that in that particular direction, there's definitely both a slow and a high velocity material outflowing towards it. And so what we wanted to do is we wanted to look towards that region to see how towards 30 Doradus looks in comparison if you go further away. And so what we're doing is that there's a study that my postdoc Suraj Pudel is leading, who is presenting a poster here at this conference. He's looking towards the 30 Doradus region, and he's finding that when we look at the column densities, right here we're looking at iron 2, when we look at the column densities, they gradually decrease in velocity further out, and it seems like there's a nice coherency out to about 100 kilometers a second in local standard rest frame. Now, this right here is looking at the column densities of the material that is within half a degree of 30 Doradus. If we were to look at further than that, it starts to get a lot more choppy and scattered, and there's not a coherent trend at all. So it looks like in the 30 Doradus region, there's this coherency. Another thing is that when we look at the column densities and we look to see how they change as a function of getting angularly farther and farther away from 30 Doradus. And so what we have here is we have angular shift, where right here we're closer to 30 Doradus. Here we're getting further and further away. Over here we have the iron 2. There's a steady drop with this as we're getting away from 30 Doradus, which isn't too surprising because remember, that's a very bursty region. That's a very active region, and we expect that there to be a lot of outflows in that particular direction. Okay, and the regions around it just aren't nearly as active, so that's not too surprising. Okay, so over here, close to 30 Doradus, further out, and if we add up how much material is being ejected out of this region of the galaxy, then we get something on the order of 0.5 million solar masses a year in this outflow in just the 30 Doradus region. So that's interesting. That's interesting. Okay, so what's happening with these outflows? Okay, so with this material, you have this slow-moving component and this fast-moving component. What is this wind doing? Is this wind consistent with what's happening with the Magellanic Clouds? Now, the Magellanic Clouds, they're coming in. We have the Milky Way. They're coming in over here. They're coming by passing the Milky Way. When they're passing by the Milky Way, one of the things that they're doing is they're passing through the Milky Way's halo. Okay, as they're passing through the Milky Way's halo, that halo is going to act as a headwind, and that headwind can act to suppress this wind. And so we see all this evidence for this outflowing material, but is this plausible also given the scenario that we're traveling through a hot halo? And so what we did, this is the earlier study back in 2001, was when we accounted for ram pressure, if this right here is the near side of the galaxy, which is the side that would be facing towards us, by the way, for orientation. So the LMC is a near face-on galaxy. this side would be facing towards us. This side would get suppressed as far as its outflows goes, and this part over here would be just fine because it would be on the backside opposing the ram pressure. Now, that's what we thought back then, but since then, there's been a few new ideas. Okay, so this is the part that we'd be sensitive to with Ulysses. One of those ideas is that it turns out that people now think that the LMC is a lot more massive, and because they think it's a lot more massive, they think that, well, the LMC itself might actually have its own halo. The Milky Way has a halo, but what if the LMC has a halo? And if it has a halo, then that can actually act as a protective shield to help it fight off some of that direct ram pressure. It acts as like a nice buffer. Okay, and that can actually help the galactic wind survive just fine. Now, I want to point out, we're going to hear another idea about a bow shock tomorrow by Young's talk, so stay tuned for that. The bow shock model also helps to act as a protecting barrier to help propagate a wind. In this particular situation, the observations are essentially consistent with both of the models. We can't actually distinguish between the two. But either way, we think that there is an opportunity for these winds to be protected. Now, if the LMC does have a protected barrier for a halo, what it would look like would be something like this. Okay, so we have the LMC over here. Normally, when we think of a halo, we think of it as being this nice, extended, spherical thing. But remember that the LMC is traveling by the Milky Way, and as it's traveling by the Milky Way, it's experiencing the ram pressure. And that halo itself, even though the winds might be protected, the LMC's halo is not protected. And so all this crazy, like weird blobbiness that you see over here, this is a distorted Magellanic corona that is being extended outwards and being stripped. But that would leave this area right here protected. And so we have the Milky Way, we have over here the LMC, and then this right here would act as like a nice little pocket that these winds could propagate. Okay. Now, there's a lot of interesting, fun structures in this region. You might have also noticed over here that there's this Magellanic stream thing. This thing is huge on the sky. It spans over 100 degrees. If you were to add up all the debris in the trailing stream part, it's on the order of 1 billion solar masses of gas. If you were to add the bridge and the leading part, then it'd be on the order of up to 2 billion solar masses with neutral and ionized gas. These things, these structures in the sky are humongous. One of the things that we wonder is, how are these structures created? Okay, so this is some work that my graduate student April Horton's leading. You heard from her yesterday, and she has a poster that's up. And so a lot of the slides you're going to see are taken from one of the talks that she created recently. Okay, so one idea is that when we look at this stream, one thing that could create it is that if we had this outflow, some of the outflowing material could actually go and feed into this stream over here. Now, do we have any evidence for that? Okay, so along the trailing stream, it turns out that there are two filaments. There's one filament that happens to be a low metallicity one. They're spatially separated from each other, by the way. One that's high metallicity, and they're coherently distinct from each other kinematically. And so they look like they're different things. When we trace back where they came from, one of these filaments traces back to the lower metallicity SMC/Magellanic bridge region, and the other one traces back to the LMC, the higher metallicity area. And it looks like it might actually even trace all the way back to 30 Doradus. Okay, so what April's doing is she's looking in this region over here, and she's using the Ulysses observations to get an idea if we can detect the stream at all. And if we can detect the stream, then what that would tell us is that this stream could trace back to this region, and that stream lies on the front face of the LMC. Right? Because that's one of the things we can say, we're only sensitive to material on the front side of the LMC. And that can help us to make better predictions for how in the world the structure is made using galaxy interaction simulations and fun stuff like that. We can do some constraining. Okay, so here's this region that she's focusing on. So we have 30 Doradus over here in this corner. Here are some of her sight lines where she's using Ulysses data sets. And what she's finding is that when we look at this position velocity map, so we have position longitude on this axis. Right here, we're looking at velocity, and I'm showing you H1 column density. Okay, so we're looking at a whole bunch of vertical spectra, essentially. Okay, and there's this coherent structure here. That coherent structure is going to be the disk of the LMC. There's something over here. Okay, and this is just showing you where the overdensities are. Okay, where these overdensities are. This black line right here, this is what is predicted based off of David Nidover's 2008 work when he traced back the filament kinematically. He predicts that the stream would have this velocity here. And he did that using low angular resolution lab survey data. So it has a 0.6 angular resolution. This stuff, I can't remember the angular resolution off the top of my head, but it's tiny. It's very tiny in comparison. Using gas cap observations, by the way. And then this right here, this filament here, it's pretty close. It's pretty close. Okay, so we have this over here, we have this disk. And right here is where we predict the Magellan stream to be, based off of these observations. Now, what do we see in absorption? Okay, so here's what we have in absorption. We have a nice spectra over here, velocity over here, so Doppler shift corrected, normalized flux. We have this awesome feature right here, Milky Way. Go Milky Way. We have over here the Large Magellanic Cloud Galaxy, and then we have this big, huge absorption feature right here, which we would associate to be with the Magellanic stream. Okay, so if we were to map out all of where she found the stream to be at kinematically, over here we have velocity on the x-axis. Over here, we have offset from 30 Doradus, so closer to 30 Doradus is over here, farther is over here. This is tracing where the H1 is for the LMC's disk. This over here is where we would trace the H1 of the Magellanic stream to be, so the emission. And here's what the predicted would be from the David Nidover's 2008 work. And here's what we find in absorption, specifically for the stream. We find these components over here. Okay, so this is providing us with compelling evidence that the stream lies in front of the LMC. It's pretty cool. It's pretty cool. And it does tracing back over to the 30 Doradus region. Okay, now, with the stream though, one of the things I can say about it is that the gas flow is redshifted. And so there are some alternative theories floating around, whether or not that's associated with a trailing stream that's with the tidal stuff, or maybe there happens to be some inflow material that's feeding the 30 Doradus region to cause bursts in star formation, because 30 Doradus is very bursty. We can't distinguish between those two scenarios, but either way, it's tracing back, so that's very cool. So, to summarize, I'm leading a big, huge Hubble Legacy Archive project to explore the winds of the LMC outflows. We find that there is a pretty good amount of material getting kicked out of this galaxy, and this outflow rate will depend on whether or not you're including both the slow-moving and the fast-moving components of the wind. Okay, so this right here will be including both of those components. Towards the 30 Doradus region, we find that the winds happen to be very, very strong, and that they might behave a little bit different as you move away from them, as you move away from this region. And we find that there's evidence that the 30 Doradus region has some kind of connection with the Magellanic stream that needs to be sorted out a bit. All right, and with that, I'll take questions.
We have time for one question, maybe two.
Very nice talk. So most dwarf galaxies are known to have outflows. How would the outflow of the LMC compare to the outflows in other galaxies? Would it be fairly typical, or would the proximity to our galaxy make a difference?
Yeah. Okay, so that depends on a couple of things. Okay, so one, it depends on if you include the fast-moving and the slow-moving component of the wind. And if you include both of those things, compared to the star formation rate, usually people calculate the mass loading factor, and it's an eta symbol. So that's essentially the outflow rate over the star formation rate. If you include both of those components, and you'd predict something on the order of 4.5 for that, which means that the outflow is 4.5 times more efficient in comparison to the star formation. You know, you can kind of think of it like that. How that compares with other galaxies, what that would mean is that when you look at how well you can get outflowing material for galaxies, there's like this fun linear relationship where you have a situation where outflows seem to be easier to do in small mass galaxies, which isn't too surprising because it's easier to throw things in the air, right? You don't have to throw as hard to escape out of a small galaxy. And then the outflow, that eta value changes as you migrate to higher mass galaxies. And then for the LMC, what we would predict is that if you were to look at that linear trend, we would lie above that trend line, but that would be probably because when we were doing that emission line study in H alpha, we were able to see about a factor 10 more sensitive than other studies can see. So I think it's more of a matter of sensitivity and less something that's atypical with the Magellanic clouds. And the other thing that I wanted to mention though too is that we have to be careful when we think about what kind of galaxy the Magellanic clouds are, because back in the day we used to think that they'd have masses that were on the order of, for the LMC, 3 times 10 to the 9 in solar masses. But we now think that the LMC might be 10 times more massive. So back in the day we thought it was 1/100th the mass of the Milky Way. Now there's observations to suggest that it's only 1/10 the mass of the Milky Way. So this thing could be very far from a dwarf galaxy. Just keep that in mind. So and the SMC is about 1/10 that of the LMC, and it follows the same trend. You know, if the LMC gets more massive, the SMC gets more massive. Yes.
I'm sorry, I need to
Sure.
I need to stop you here. We don't have time for more questions, so let's thank Kat again.
Okay.
And next speaker is Dory Cheesy. It's you. There was a change in the program. So the latest version of the program, by the way, is on Slack. I hope you're ready.
That's a Mac.
Sorry, I don't know how this works.
Okay. Oh, no worries. Something went on. It's a Mac.
We can see the layout.
Okay, people, how do I make this full screen on a Mac?
We have some help here, don't worry.
Awesome, thank you.
All right. Thanks, Dory.
Can you hear me, everyone? Yeah?
All right, hi everyone. My name is Dorothea Secchi. First thing first, do you want to learn how to pronounce my name? Okay, so instead of Dorothea, you can say Dory, like the fish. That's pretty easy. And as for my last name, what do you tell someone if you want them to smile for a photo? You tell them, say cheese. That's my name, just without the Z at the end, say cheese. All right, with that out of the way. So it's a truth universally acknowledged that many people use stellar evolution models in their research. Maybe even you. Hands up who has ever used stellar evolution models in their research. Wow. Okay, so I think you're my audience here. Now, I'm a massive star person, so today I only want to focus on massive stars, meaning stars more massive than 8 times the sun. If you are using low mass stellar evolution, ask someone else. That's not me. I'm only talking about massive stars. Now, there are, of course, many libraries or so-called grids. For example, the Geneva libraries or the Bond grids or many other that I'm going to mention in this talk later, available online that you people can just go there, push the button, download the tables, and use it in your research. That's a thing many people do, and that's completely fine. Another thing that many people do is, these days, you can do it yourself with Mesa. Hands up again. How many people have used Mesa? Okay, a little bit less, okay, but still quite a few of you. Now, with this approach there, it's great because, I mean, you can download the code, you can push the button, you can just really create your own stellar model, but still, you would need to interpret it, right? You would need to know what the various things mean. So that's not necessarily straightforward. But these models have a quite wide range of usage. Here are just a couple of examples that I could come up with from the top of my head. For example, one can try to obtain mass and age of the observed star that you want to. You have a measurement, an observed star, and you want to derive a mass and an age, so you use a stellar evolutionary model to give you that and fit it to the observed parameters. You can use them in star formation simulations or star cluster formation studies, so many other things. You can use it in the chemical evolution of the universe, for example, because of the stellar wind feedback or the supernova feedback. And of course, one of my favorite usages is binary population synthesis, because we want to predict the number or statistics of gravitational wave events. So all these and many, many more, I'm sure, are ways people use stellar evolution models. So please, if you want to tell me what you do especially, come to me after the talk. I'm very happy to discuss things with you. So the issue with this is that the models are, for many of you, I'm pretty sure, just a black box, right? Even if you download Mesa and create the model for yourself, even if you're not using a pre-existing library of models, you're still using it as a black box most of the time. And it's normal. There's nothing wrong with that. I mean, you are an expert in whatever you do, streams of Large Magellanic Cloud outflows or whatever wonderful things. You don't need to be an expert in stellar evolution. That's fine. However, this is why I'm here today. This is what I want to tell you today, because let's peek into the box and let's see what's inside the black box. I'm sure you not do that often. So we have this paper out with my ex-PhD student, now postdoc, Poojan Agrawal, from 2002 in Amandras. And there are, of course, many other papers which investigate the same kind of problem with the black box. Here are 2 more examples that you can look up if you want. But today I want to tell you about our own paper, because I think it's really fascinating. So what we did, we just simulated you. We simulated what happens if you go online, look up 5 existing stellar libraries that are available online, you download the data, and compare the models just to see if they give you the same results, if they give you the same predictions, right? That's a straightforward thing to do. So yeah, we simulated you, and we looked up all these 5 existing libraries, the Padova code, so-called parsec, the MIST project, which is a Mesa-based project, the Geneva models, the bypassed models, and the Bond code, basically the BOOST project, which is my own project. So we basically downloaded these 5 model sets and compared them. Very important caveat, we are only comparing models with the same mass and composition. So basically what we are doing now here, single stars without rotation, so either slow rotation or no rotation, so a low rotational rate, and the composition is solar. We did that because we just wanted to have this first glance of how the models look like. But we would really love to do that later on for other metallicities. It's a work in progress, and other rotational rates and everything, and even binaries. That's a big headache to do, so I don't know if we ever get there. But for now, this is the parameter range that we are talking about. Just keep in mind. Okay, so here's the result. Now, so this is a 25 solar mass model. Okay, so this is a massive star, an O star. At least it starts out as an O star on the main sequence. And the 5 lines that you see, of course, this is the Hertzsprung-Russell diagram. I'm sorry, this is the luminosity displayed here. So the 5 lines you see are coming from the 5 simulations, the 5 codes. And I mean, this is not bad, right? I mean, this looks good. This looks like the models are pretty much doing the same thing. There are various discrepancies. For example, the end of the main sequence region is kind of shady, and I mean, it's not clear whether the stars have a blue loop or it's blue supergiant phase or not, and the red supergiant phase is not properly covered the same way. But like, you know, more or less, at least, especially the main sequence, which is maybe the most important phase, it's a good fit, right? So there's no problem. What if we go to different masses, though? Because at 25 solar mass, I think we more or less understand stellar evolution, sure. But at 40 solar mass, the situation gets much, much more muddier. At 80 solar mass, it's insane, and at 100 solar mass, it's just all over the place. And when I first saw this picture, I was like, oh my God. Okay, I kind of expected it because I'm a stellar evolution person, so I had something like that in mind when we started the project. But like, I think looking at it like this gives you a pause. Like, what's happening here? Why is even single star evolution at solar metallicity so uncertain? What is that we still don't understand in these codes? What do these codes do that explains this variety of predictions? And maybe most importantly, which one to use in your own research, right? Here are a few of some other predictions. I don't really want to go into that. So here we just compared some other things, not just the Hertzsprung-Russell diagram. So here we are comparing radius, maximal radius, because it's important for binary research. And here we are comparing final mass as a function of the initial mass, just to see how the 5 sets of tracks behave. And as you can see, there are discrepancies, especially at the higher masses. So, okay, but why is this? I have a quick and dirty answer for you and a long and complicated one. The quick and dirty answer is that, well, we don't really understand massive star physics yet. The reason for that is that basically there is not enough observations of very massive stars so far. I'm really hoping that Ulysses will help with that a lot. That's one of the reasons I'm very excited about this whole collaboration. But so this is an older survey from the paper is from 2018. It's from the VFTS survey, and as you can see, it was a massive star survey from the Large Magellanic Cloud. But you can notice here right away is that the region where we find the discrepancy amongst the stellar evolution models is the exact region where there is a drop in number of stars. So basically, we don't have enough observations to constrain the models against. And that's the main quick and dirty reason why we have so many uncertainties in the models. And yeah, and as I mentioned before, this region up there, this very massive star region, matters. Because these stars are ejecting material in a crazy way. Like, they are really pushing away stellar material during their lives. They influence the chemical evolution of the universe. They explode as supernovae or not, who knows, form black holes. those black holes might merge in a gravitational wave emitting merger. So yeah, these objects are really, really important, and we still don't understand them. All right. And do you want to hear my long answer? Let's see if I can make it accessible. So, to understand the long answer, I have to ask you a question first. What is a star? Okay. I want to hear, are there any PhD students in the audience? No PhD students? Okay. You?
Oh, yeah. It is a gas cloud that is engaged in nuclear fusion.
Oh, very good, yeah. So we have a gas cloud, very good. I would say it's a sphere of gas isolated in outer space. So basically a hot, dense plasma, sphere of hot, dense plasma, okay? Yeah, I spoiled the answer to the next question. Why is it, what contributes to its stability? Because it's stable, right? We see the sun, it's stable for millions and billions of years. It's a stable glass cloud in space. Why is it stable? I already spoiled it for you. It's stable because we have two forces acting against each other. We basically have the pressure gradient, so the internal pressure of the object. It might come from the gas pressure, it might come from radiation pressure, whatever pressure, but it's a pressure that keeps it intact. And the gravity, or the self-gravity of the object pushing inwards. So these two forces create this very nice equilibrium, which is a very long-lasting equilibrium, we know, because you look up at the sky and you see stars shining for millions of years. So that's a star for you. Okay, next question, just out of interest. Where is the surface of this object? Because it's a cloud of gas. There is no box containing it, right? There is no container. Where is its surface?
We don't know. Wherever the wind finishes.
Yeah, we don't know. That's right. That's right. And she's a multi-star person. She knows. We don't know. The thing is, we usually say the surface is where the photons escape. That's the so-called photosphere. But still, it depends on the opacity and it depends on the frequency. So it's really, really complicated in practice to define the surface. Okay, so this is what we see. The photosphere is where we see the photons coming from. Okay, next question. What is inside? How do we know what's inside? I heard nuclear fusion before, so that's good. How do we know why do we know what's inside? What is the main method?
There's neutrinos that we receive.
There are neutrinos, yes, that's very good, there are neutrinos, and also we can have these days astroseismology, which is another great tool to observe the interior parts of the star. But historically, for decades, the main tool of peeking into the star was the theoretical modeling of the stellar structure. Now, what does it mean? Basically means this. We have these four rather complicated so-called stellar structure equations, which is a set of partial differential equations, but it looks more complicated than it actually is. Because the first one is actually tells you about mass conservation. It's basically the physical law of mass conservation. The second one is momentum conservation. Very simple physical principle. The third one is energy conservation. And the fourth is some kind of transport of energy. So with these four basic physical principles, plus adding many, many more assumptions, like equation of state and so on. But basically, based on these four differential equations, we can compute the structure of the star from the center out there to the surface, the whole structure of the star in every point between the center and the surface. And then by changing the composition due to nuclear burning, which is done by this fifth set of equations, we can simulate the whole evolution of a star from birth to death, right? So we compute the first four equations, then change the composition, which means change the time, so you have a time step, and then you compute the first four equations again, and so on, and so on, and so on from birth to death. This is stellar evolution. This is how we computed these tracks on the diagram. All these tracks here were computed with these equations, basically. And yeah, so I think it's a pretty good fit, especially here, down here. But as we discussed before, up there, well. Okay, and the main question for now today is how much more time do I have?
You still have time.
Still have time,
Something like 15 minutes.
Because this is the hard bit.
Or 10.
Now that we understand what stars are and what leads to the long-term equilibrium, now let's figure out what happens if the equilibrium is compromised. And that brings me to the question of the Eddington limit. We heard about the Eddington limit yesterday in quite a few talks. Hands up if you don't know what that means. Okay, I don't want to ask this because that's embarrassing. Hands up if you would not be able to explain to an audience what Eddington limit is. That doesn't mean that you don't understand it, but okay, at least one brave person. Very good. Anyway, I'm going to explain it now. I will try to explain, and Yori can always stop me if you think I'm saying something wrong. But so basically, the Eddington limit is what we just discussed before. This equilibrium between the internal pressure and the self-gravity compromised. And that can happen because the star is can be way too luminous. Massive stars can have so much energy generation that the luminosity becomes so high that the internal pressure is basically pushing the star apart, and gravity cannot keep it intact anymore. This is what the Eddington limit is. Of course, it's also much more complicated because you can define the Eddington limit either on the surface or you can define it in every point inside the star. So it gets much, much more complicated, but this is the main concept behind it. And it's very important for us massive star people because if that happens, then we need to deal with that somehow. Because if the equilibrium is compromised, those stellar equations that I just showed you cannot really work properly anymore. Because those can require proper stability. Yeah, so there are other reasons actually for falling out of equilibrium. The Eddington limit proximity is one of the reasons, but there are other scenarios. For example, I'm sure you've all heard about an iron core collapse, like when a massive star finishes its life, then we have an iron core formed, and the iron being the more stable element, it cannot be burned, it cannot be fused into anything else. So basically, gravity wins and the star collapses. That's another time the star falls out of equilibrium. And yeah, we have the pair instability process, which I'm not going to explain now. And yeah, so there are various phases of the star's life when the equilibrium is compromised. One is the Eddington limit. Okay. So the consequences of approaching the Eddington limit for the stellar interior are basically kind of explained here, or just presented here. So what happens if okay, so how should I explain this? So this is the center of the star, and this is the pressure inside, and this is the surface of the star, okay? So this is the core where the pressure is high, and this is basically the envelope where the pressure is low. And up to this point, it looks like a normal star, but this peak here should not be there under normal circumstances. This peak is here because these regions reach the Eddington limit. These regions are way too luminous, and they try to, I don't know, yeah, so it's, the stability is kind of compromised here. So it's called a density inversion, and this is something that some of the stellar evolution models predict to happen when the Eddington limit is reached. The reason for that is that the energy transport is not efficient enough at this point, and so basically convection is very weak. And that leads to this whole big envelope, and this is called envelope inflation. If you never heard about it, don't worry. what I want to say with this is that this is a numerically difficult situation that most code cannot deal with. And if you, for example, use MESA and want to simulate a 40 or 80 solar mass star at solar metallicity, you most probably will encounter something like this, and the code will most probably just stop working, like break down. And this might very well be the reason for that. It's all explained in our paper, so if you want to have a deep dive into this, then you can just read up the paper. I think it's very well explained there. So how do the codes deal with this numerical difficulty? So we found that various codes treat this using various tricks, kind of, like pragmatic solutions, I would say, not trick. Yeah, so for example, in the Padova models, they are artificially limiting the temperature gradient, which is like a pragmatic solution. It works, sure. In MESA, at least in this MIST project, they use the so-called MLT++ formerism, which is another way of not reaching the Eddington limit and avoiding these envelope inflation and density inversion things. But whether if it's real, whether if it's, realistic, whether that's what nature does, we don't know. It's just a pragmatic solution that coders, that developers apply to solve this numerical challenge. But who knows if it's true or not. So in Geneva and Bypass, at least in the models that I showed you before, they use an artificially enhanced mass loss at the right moment. So they just basically say that, all right, those layers on the top, those renegade layers, they don't want to belong to the star anymore. So let's just remove them. And they do. And that might be so. That might be what the stars do. But we don't know. And finally, in my own project, I developed a way of overcoming this step. You can read it in my paper if you want. Okay. Anyway, so the various codes do various things. And I'm at the end of my talk, actually. So this is some more results about the ionizing flux. We also computed that. So if you're interested, just look up in the paper. We also computed differences in the remnant mass. And we found that there might be up to 20 solar mass difference in the prediction of the black hole mass that we predict, which is quite a lot, which is frightening. Yeah, and this is my conclusion slide. So what we learned today by peeking into the box was that, first of all, Eddington limit is a thing. Stellar evolution above 40 solar mass has not yet reached consensus. So, not even at solar composition, and I didn't even touch low metallicity. So, like, yeah. My solution to this problem right now for you is to please use any stellar models with extra caution and be flexible for updates, because updates are coming up. My community is actively working on this problem. We are really pushing for solutions, and there are updates coming up in the near future, hopefully. But please be flexible. So just because you downloaded the Stellar library 3 years ago and you're using it and you're loving it, don't suppose that this is the final answer to all your questions, because it's probably not. And there are new models coming up with better physics. And yeah, I think my most important takeaway message is that if you decide to do it yourself with MESA, ask an expert before publishing anything, okay? Very important. Don't think that you can do it alone without an expert. Even better, hire one. If you have money in your group, it's a great thing to hire a stellar evolution expert, because we know our stuff. You don't have to know it. Here we are for you. Okay, and I'm done. This is the postdoc, ex-PhD student I was talking about. She's responsible for the project. She's great. She's working as a postdoc in the US now. And this is my small stellar evolution group in Poland, in Toruń. And I'm actually hiring this fall. So if you're a postdoc or a PhD student looking for a postdoc job, I have a 2-year postdoc position opening this fall. So maybe your face can be there later on. Thank you very much. That was it.
Hello? Okay. Yeah, so while we take one or two questions, may I request Solly Hip to please come and set up? You're next. Solly Hip?
I don't know if she's aware that the program was changed.
Yeah, so there has been a change in the program. And, okay. I encourage everybody to check for the latest version of the program, which is in Slack.
Thank you very much. Can you hear me? Yeah. Thanks for being so open with the treatment of the convection. I really enjoyed that. Now, I guess this is a little bit more of a comment, but I'll take my opportunity to say it. The problem with all of these is that they're physically wrong. But if you want to treat the outer boundary correct to get rid of these problems with the Eddington limit, I mean, we have actually done the calibration of that now based on the 2D models for those stars. Mm-hmm. And what you need to do is that you need to invoke the turbulent pressure, and you need to also actually invoke the wind, not like you take off mass, but as an active outer boundary condition, like we do in the 1D stellar evolution models. And I'm betting you, if you just update the outer boundary conditions in the evolution codes to that, they would agree, presuming that the overshooting, core overshooting and stuff like that. So my plea to the stellar evolution community, since you are that please, can we do this together? Because since we're busy with the atmospheric model calibrations, we don't really have time to do it ourselves. But I mean, inclusion of turbulent pressure, and then I think this will take care of it.
Awesome.
To be honest.
Yeah. Okay.
To be honest with you, instead of using the various fix-ups that I know that we're using now, I'm also using them. So.
Thanks.
Sorry for not having a question, but it was just a little bit of a plea.
Okay, we have time for one more quick question. Maybe, do we have questions online? No. Okay, we have one question in the auditorium.
A quick question from the point of view of a cool star person. I was once told that when you had something you can't explain, invoke magnetic fields. Do magnetic fields have any role to play in hot star evolution?
Oh, that's a good question. I think in these models, magnetic field was not included. I think. I would need to look it up. But magnetic fields are not that important for massive stars as they are in low mass stars. So as far as I know, about 20% of massive stars are magnetic. 80% are not. So some people are working on magnetic fields because we do want to understand magnetic massive stars, yes. But most massive stars don't seem to be magnetic. So we just don't include that in the simulations sometimes, yeah.
Jörg, I think you will have to leave this for the coffee break. Well, thanks, Dory, Seichi. Sorry about that.
Very nice, Laura. And how does this work? Oh, this is, but,
Do you have a presentation?
excuse me?
You have a presentation on the computer.
Yeah, I just need to know where how do I control the slides?
This is also yours.
That's it.
You need to push the big button to move the
Okay.
slides.
Uh-huh.
Which one is the pointer? You're doing this.
Okay.
You will have the clock here,
Okay,
counting the time.
yeah. Uh-huh. I wrote out I talk just to see how long it would take. And so I can guarantee that it will be done in 12 minutes, unless I ad-lib, and then it could take all night. So, in order to attack the big questions about star formation and evolution, questions like the initial mass function for massive stars. We need to have in hand the fundamental parameters of stars. It is generally recognized that the three fundamental parameters determining the evolution of a star are initial mass, metallicity, and rotation. We can infer the metallicity and rotation rate from observations, but we can't infer the initial mass or age directly from observations. That takes forward modeling with checks and refinements from observations. I'll show an example of the process involving theoretical spectra of isochrones at various ages. There are two steps to getting to the spectral library. One is the construction of isochrones. The University of Geneva has taken the lead in computing isochrones of massive stars by interpolating in the evolutionary diagram that you see at left to measure the properties of stars at different masses at a given age. You can obtain from their Cyclist website a chart of all the properties of an isochrone at the age you supply, and they do it within 1 minute. It's really amazing and helpful. Step 2 is the calculation of the spectra, and that's Yvonne Hubany has calculated model atmospheres in spectra running from 200 angstroms to 10,000 angstroms with a resolving power of 20,000 to match the cost spectra. There are more than 2,000 spectra in the library for the various metallicities encountered by the Ulysses project. That's not enough, we found out. There's a big gap between 5 and 10 million years, as you can see there. But we'll try to fill that gap in the near future. Okay. Now the example I want to show you is this problem that unearthed by Nolan Walborn. How many of you knew Walborn at the Institute? Yeah. He was my office mate before he came to the Institute. So I've known him for a long time. The problem that he unearthed is the fact that there are two maybe there's a pointer, I don't know. Two stars here on the HR diagram. AB83, which is a robust 1AF plus star, and then AB69, which is a mild-mannered giant. So the question is, how do they both evolve into the same spot? Well, John Hillier picked up on this question and found that the main difference between the two stars is that AV83 is a rapid rotator and AV69 is a slow rotator. But the study didn't go on to obtain an initial mass or age for the two stars, and that's what we'll do today. So, first of all, what happens with rapid rotation? And here I'm showing effective temperature against log of the luminosity. And it is not an HR diagram. Alan Sandage called it the banana peel diagram for obvious reasons. So the banana peel plot shows how how the isochrones here change the properties of the star. I've shown in small dots non-rotating stars and big dots rapidly rotating stars. And up in the middle, there AB69 appears to be very close to a non-rotating 5 million year isochrone. But AB83 is nowhere close. It's much less luminous than where the rapidly rotating stars should be. So, the following this picture, we can see that AB83, well, as time goes on, stars are less luminous and somewhat cooler. And so to match the AB83 onto a onto the proper isochrone, we'll have to go and choose an older age, and that's where the isochrones from Geneva come in. That you can just go and say, what instead of 5, how about 6 million years for 83? And better yet is 7 million years. And so this slide then shows where the age in the darker orange at 6.3 years, the two isochrones for AB69 and AB83 overlap. And if you adopted 7 million years, then the isochrone for AB3 would bisect AB83. And so we have a metallicity, an age, and also an initial mass. And I've shown the results here on the left side of the diagram that AB83 is a less massive star than AB69. And its age it's older, 6.3 to 7 million years instead of 5 million years. And its mass is only 26.7 as opposed to AB69, which is 34.25. You see at this lower metallicity of the small Magellanic Cloud, there's not much difference between the initial mass and the instantaneous, or the mass, the concurrent mass now. So that works. Unfortunately, we don't have a spectrum, a predicted spectrum for AB83 because we didn't know about what the age was and we haven't calculated it yet. But we do have one for AB69 that we can compare with observations. And that's shown here. This is the STIS. In black, it's the STIS shell spectrogram, and in red is our model of it. And all of the black are observed absorption lines that aren't that the model doesn't match. Those are interstellar lines. And the lines of nitrogen-3, the doublet at 1163 and 1165 on the left, and then the nitrogen-5 doublet at 1239, 1242. We don't match because the nitrogen is simply very weak. And this is what caused Nolan Walborn to say that it is an OC 7.5 luminosity class 3. That, and Hillier later determined that the nitrogen abundance was very low. This may be like Grace Telford's low nitrogen stars that she discussed yesterday. So in summary, we're close to having theoretical tools to aid the Ulysses program, and I would propose that we apply this to all the O and B stars of in the Ulysses program, so that we have initial masses and ages and can start talking about the IMF of massive stars. Thank you.
Thank you very much.
This is where I need you. Okay.
Perfect timing.
Oh,
Thank you. So we have questions.
Sally, isn't there one additional step? The evolution models assume a rotation velocity. But if you have only one star, the data only give you V sine I. How did you get the sine I?
What did he say?
How did you know the inclination angle to calculate V sine I?
Cannot be anything between 0 and 400?
For AB69, I didn't know what the rotation was. And how to, what I did was I simply applied different amounts of rotation to match the spectrum, and it was 104 kilometers per second, which is what Nolan Walborn measured. So we've got that. For AB83, there it doesn't. Its apparent V sine I is something like 80 kilometers a second. And Hillier and et al., including me and Linda Smith and Chris Evans, then figured out that this AB83 is seen nearly pole on. Does that answer your question? Yeah, okay.
We have another question by Aida.
Hi, Sally. What's going on at carbon-4 1550? Why is there that strong emission there?
Yeah, she's wondering why the carbon-4 P-Cygni profile is not fitted.
Why the carbon-4?
Yeah.
Because the line is not formed in the photosphere. This is a purely non-LTE photospheric spectrum.
Got it. Okay.
I should have
Thank you.
mentioned that.
So these are trusty models.
These are what used to be called T-Lusty.
Okay.
Thierry Lance and Yvonne Hubenes. In the meantime, Yvonne has gone on. He's plotted a lot of spectra for calibration purposes for the Space Telescope Science Institute. And we're planning to hand this over to the Institute once we're finished.
That would be very nice. Yeah. So we have time for a very quick last question. Well, otherwise, thank you very much. So I think we are breaking now for the coffee break, or are we doing the pop-up? Okay, we are doing poster pops. Sorry about this. So I have here Gunther, Walter, Singh. I'm sorry for my pronunciation.
On the agenda, yeah. So Kudish, but I think he has a video. Dory, your student, we're gonna just show the video, right? I think so. Okay. Hans, last name Singh, I don't know the first name, I'm sorry. Majidi, Louison, and Connor. So you can all line up here, and I think there's maybe another person online, we'll see.
Let me help you with that. Thank you. Let me take this. Oh, you're doing it. There you go. Thank you.
We are not using this microphone, are we?
No, we'll just use the handheld one, it's easier.
Where's the switch? Okay.
No. Is Kushik online at all? Kushik Sen? No? Okay, so he left a video. So I'll just play it now. This is Dory's student. Hold on, I'm trying to get the sound up, but I don't know how to do that. No, it's on. Oh, yeah. Oh, thank you. Nope.
Please.
The sound button of the laptops are blanked out, so I don't know how to do that. Okay, we'll do another poster while we figure that out. Is Coach Vandra here online? Okay.
Yes, I'm available.
No? Online, yes? Yes. Okay,
Yes.
perfect. They can unmute.
Can I turn my video on? Am I audible?
Yeah, can you raise the volume?
Okay, can you please increase the gain of your microphone? Is it possible?
Just a minute.
Because we barely hear you.
Am I audible now?
I cannot hear you yet. I can hear myself. But
Am I audible now?
Yes, that's good.
Yeah, okay, thanks. May I go ahead?
yes, please.
Yeah, thank you for giving me this opportunity. I'm Kushbin Singh from Tata Institute of Fundamental Research, Mumbai, India. And in this poster, I'm going to I'm presenting our recent discovery of migration of accretion hotspot over stellar surface during an outburst in EX Loopy. EX Loopy has a history of outbursts since 1940s. There have been numerous outbursts. And in March 2022, the star again went into an outburst of delta G is equal to 2 magnitude. And during that time, we monitored with a very high cadence photometrically and spectroscopically this particular star. And during that monitoring, while we were searching for something else, we realized that the phase of the light curve suddenly changed during the outburst. I hope this particular figure is visible. which is showing the phase variation of the light curve as a function of time. What this phase tells about the accretion hotspot is the light curve is pretty periodic with a period of 7.4 days, and with the uh, uh, with the uh, uh, with the monitoring of the phase of the oscillatory light curve, we can monitor the location of the hotspot over stellar surface at different point of time. And since the phase changed right during the outburst, it means the hotspot changed its location right during the outburst over the stellar surface. And this is a completely new observation. This has never been found before, never been reported before. To understand this particular phenomena of migration of hotspot, what we propose is that right during the outburst, the accretion rate increase, the disk compresses the magnetic field, disk comes closer. Now, assuming that the infalling matter is moving along. Is moving is rotating by Keplerian velocity. Since the disk has come closer, it starts rotating faster, and since star is rotating at its own pace, the matter starts to fall at larger azimuth. Basically, the star starts to lag behind the infalling matter, and matter falls at a larger azimuth, eventually creating a hotspot at a larger azimuth. And in turns, we see observationally the phase change in the light curve. With the same correspondence, we see the phase change in the radial velocity of these the spectral lines which are forming in the hotspot. I hope this is visible, where these squares are showing the radial velocity phase for before the outburst, while these color points are showing the spectral radial velocity phase right during the outburst. We saw that there is a corresponding phase shift or the hotspot location change observed right during the outburst. To complement this particular observation, we further performed 3D MHD simulations, which reproduced a result of hotspot migration over the stellar surface right during the outburst. Thank you.
Thank you.
Yeah.
Okay, hi everyone. My name is Jada Luison. I am a second year graduate student at the University of Massachusetts, Amherst. And I am presenting a 2-year study using Keck's low resolution imaging spectrometer. And so the whole poster is not showing, but we have a sample that was originally, thank you, inspired by Gregory Herczeg's sample. So our sample doubles his into a lower mass regime across a broad multi-wavelength range. And our case study for our preliminary results is that we have Dennis J, if you can scroll back up. Yeah, thank you. We have our first object, Dennis J 1606. And for this, I did some model fitting. The pre-shock and post-shock models were made by Connor Robinson, who will be going in a little bit to talk about his work. And so some of my next steps for model fitting is to measure accretion rates for this object. And if you could go down to line fitting, thank you. So I also did some line fitting, and my line flux values, they complement Greg's published values. And so I'm going to do some line luminosity measurements and eventually get accretion rates there. So some future work is to get these empirical line luminosities for all of our objects. And if anyone in the room has any expertise on pipette, we are trying to sort of optimize our data reduction process, particularly like ensuring consistency with like the new and old LRIS instrument. And lastly, if you can scroll down, thank you. We also have Sarah Betty's near-infrared SOAR work. Sarah Betty's here at Space Telescope. So her work is going to be complementary to our work. Yeah, that's it.
Thank you very much.
I'm going to go with Connor.
Hello, my name is Connor Robinson, and I work on accretion on young stars. And today I'm going to be advertising a little bit about an upcoming proposal for a new space telescope which will obtain UV and optical simultaneous light curves at something around a 2-minute cadence for about a month straight. The motivation for this project, or that we're motivating our science objectives, is to measure the ratio of the truncation radii to the co-rotation radii, because that tells us a lot about how stars gain and lose angular momentum during the T-Tauri phase. And so my work here that I'm presenting is basically taking some models of accretion onto young stars, looking at them in color magnitude diagrams, and from those diagrams we can infer truncation radii, basically just by, as material falls from a further point in the disk, the radiation gets bluer as the material strikes the star and heats up a spot in the star. So a lot of my posters are talking about sort of the feasibility and the requirements that we need to reach signal noise-wise in order to accomplish these objectives. So please feel free to come chat with me about the mission. The mission is called SMEX. Hopefully we'll be putting a proposal through in the next year or so for that, so stay tuned for that. And if you are interested in becoming involved, please chat with me. We're still relatively early in this process, so we're welcoming ideas in terms of what we can do with such a spacecraft. Thanks.
Small file, large file?
The big one is good.
Okay.
My name is Moritz Günther. I claim to be probably the most experienced captain of Roman river warships in this audience. And you'll see me up there working the benches in the exact same t-shirt I'm wearing right now. I've only listed co-authors by name who I can tie to work on Roman river warships. So there's Christian Schneider in the front left there. But other people have contributed to taking this data. They have, just as far as I know, never wrote on antique warships, which is why they aren't listed there in person. So Christian gave a talk and showed you X-ray data that was taken close to simultaneous contemporaneous to Ulysses data. His data was taken with XMM. We've just split the work. He proposed for the European telescopes, and I led the proposal for the American telescopes. So here's Chandra data, and then at the very bottom is NISA data. We'll start with the bottom, because if you could just go down, thanks. The NISA is the Neutron Star Interior Composition Explorer. It's an instrument that sits on the ISS, and it's really made for bright sources. Typical count rates are like 100 counts a second or so. Our stars have about 1 count a second, and that means things like a 20 counts per second background that normal people don't care for is about a factor of 20 higher than our signal is. So we need to worry a lot more about background than most people do. And the NISA team has recently, like a week ago, released a new version of their background model that looks very promising, but that I haven't quite worked through yet. So I'm going to do Chandra. This is a Chandra bit in the middle. And so the thing that we have in Chandra and in XMM2 when we have enough counts is we get these helium-like triplets that Christian already explained that are density and temperature sensitive. TW Hydra has been observed about a dozen times with Chandra and XMM. So for every one of these observations, I can measure this ratio between the F and the I line that gives me the density, and the ratio between the R to the F plus I line that gives me the temperature, and I can put it in a temperature density plot. And if you go out to the poster number 5, then you can actually see it, whereas in the resolution of the projector, since this is made for a poster, it isn't quite right. But there's a number of these here, and you kind of see like a trend where higher temperatures also mean higher densities. I'm not quite sure why that is, but you also see that the individual error bars are fairly large, and that's because every observation is only about 10 hours long. Space, like the effective area in Chandra for these things just isn't fantastic. Okay, but for some of those, we have simultaneous Ulysses data, and just like Christian had for his BP tower observation. So for example, this yellow one here corresponds to this carbon 4 line profile. This black one here corresponds to this black carbon 4 line profile. And what you see is the two that are the densest and hottest in Chandra are the top and the bottom in the carbon 4 line profiles. So if there is anything, any correlation, it must be very subtle, and I haven't been able to work it out yet. And so I think what that tells us is that the Ulysses, the carbon 4 line profiles, the far UV, probes a different part of the accretion stream than what we see in X-rays. And it's probably something to do with having streams that have dense interiors and not so dense outsides and things like that. My time for this is over, but there's more on the poster, and we have 2 days left to talk about it.
Thank you.
I can see. Yeah, I need to put sound preferences. My old man eyes aren't letting me do this. Does it have audio with it? I'm not kidding. Yeah, okay, so we're gonna do this real trick that you guys are gonna love. The old-fashioned way. I'm gonna hold a phone up to it.
A microphone or a phone?
We'll do a microphone instead of a phone, but I was thinking phone, so I'm gonna call in. Are you ready? Let's see, where's our speakers at? I'm so sorry, guys.
I think we need to start over now.
Where's the speakers?
Result in an optically thick wind from the strip star.
Life of an AV guy.
Hi everyone, this is Kaushik from Nicholas Copernicus University in Turin. Today I want to talk about the observable properties of hydrogen-rich full-fat stars in the main sequence that originate from massive binaries in the Large Magellanic Cloud. These are the so-called WNH stars. While the most luminous WNH stars may be a product of single-star mass loss via stellar winds, there does exist a subpopulation of WNH stars at luminosities where stellar winds are considered too weak to produce the Wolf-Rayet feature on the main sequence. But if you remove the outer envelope of a star by binary mass transfer, then you end up with a star which is similar in luminosity but much less massive. This increases the Eddington factor of the strip star, and the higher Eddington factor can drive a much stronger stellar wind, which can result in an optically thick wind from the strip star, which can show emission lines. Now, we use an analytical expression to estimate this optical depth parameter in our stellar models and find an empirical limit above which our strip donors can be observable as a Wolf-Rayet star. We find that strip donors up to a log L of 5 can be seen as a hydrogen-rich Wolf-Rayet star in the LMC. The short orbital periods and high radial velocities that our models predict imply that they should be readily observable, even though the toners can be more luminous than the accrete.
Dory, you brought the poster, right? It's in the cafe? Oh, just online? Okay, so, and I know it's in Slack, in the poster channel. Yeah, okay, cool. Do we need to reverse the setting of sound?
Okay, so are we done for the afternoon session?
Yes, we are done.
For the first afternoon session, sorry.
So now we're gonna go take a, yes. Let's go take a group picture, meet in the lobby. We're gonna take the picture out front because it's nice out. And then we'll have coffee break. Back at 3:30, correct. And if anybody has like a really fancy phone, better than a Pixel, let me know because that's what I'm gonna use for the picture.
I'm going to be doing something else here for a second because I want to do a little test that won't affect you guys.
Okay, all right, so you don't need my help, you're good to go?
Yeah, this will just be something I'm going to do. So, this is
Hi everyone, this is Kaushik from Nicholas Copernicus University in Turin. Today I want to talk about the observable properties of hydrogen-rich full-fat stars in the main sequence that originate from massive binaries in the Large Hadron Cloud. These are the so-called WNH stars. While the most luminous WNH stars may be a product of single-star mass loss via stellar winds, there does exist a subpopulation of WNH stars at luminosities where stellar winds are considered too weak to produce the Wolf-Rayet feature on the main sequence. But if you remove the outer envelope of a star by binary mass transfer, then you end up with a star which is similar in luminosity but much less massive. This increases the Eddington factor of the strip star, and the higher Eddington factor can drive a much stronger stellar wind, which can result in an optically thick wind from the strip star, which can show emission lines. Now, we use an analytical expression to estimate this optical depth parameter in our stellar model.